Okay, thank you very much, and it is definitely an honor to be here. My topic today is considerations on the development of robust designs. So robust design is a common term. I'm sure all of you have heard like, oh, this is a robust design, or this is a critical project, it needs a robust design. And it is a term that applies to everything, to dams, to pipelines, to slope stability, bridges, equipment, like every kind of equipment, and even software. I'm sure I'm not the only one who got frustrated one day because software crashes and it's not working. So a robust design is something that is important for everything. So that's what we're going to explore in this presentation, is what it is and what we need to do to develop our robust designs. And for those of us working in tailings, this has become like a pretty common conversation, a pretty common topic of conversation since the global industry standard for tailings management, or GISTM, because developing a robust design is one of the requirements. So we put it there as principle 5, develop a robust design that integrates the knowledge base, so everything you know, including case histories, to minimize the risk of failure to people and the environment in all phases of the project lifetime. So it was in the GISTM, but obviously that definition also applies to everything else that we do. So since then, I've been asked several times, what is a robust design? So that's what we're going to do today. Will be an attempt to answer these questions and start a discussion on what is required to develop a robust design. So there's lots of definitions of robust design in the literature. So I propose the following wording. Robust design is a practical, fit-for-purpose design that's not overly sensitive to changes and uncertainties, and its performance is, if its performance is less than adequate, it can recover or be mitigated relatively easily. So note that this is not the same as a conservative design. So that's what a lot of people ask and think that, well, if I make a robust design, is also conservative and also expensive. So I came up with a very simple example to explain that. So it is a nice warm summer morning, and we keep on having the faith that this will eventually come, but let's say it does, and you are leaving for a day hike up in the mountains. So if you go like that, short sleeves, clogs, all you take is your mug of water, that's not exactly a very robust plan. But if now you got hiking boots and hats and sunglasses, and you have backpacks to carry some extra clothing, some water, some food, maybe a small first aid kit, I think we would all agree that's a bit more of a robust plan. Now, if you add winter parka and goggles and winter gloves, like that's a bit of an overkill. So here's a risky plan or design, a robust design, and an overly conservative design. So it's a very simple example, but I think it captures the essence of what is being a robust design without being overly conservative. So as this definition is, it's a design that applies to everything and can handle the uncertainties and the variability that is absolutely inevitable in geotechnical engineering. We don't know everything about this stratigraphy in detail, and even if we detect one layer that's continuous, properties can vary a little bit from here to there. So it is particularly important. And by the way, it's an old concept. We're not talking about anything brand new here. And it is a type of design that allows us to manage risks without excessive costs or conservatism. That's practical to be implemented. And from the start, we already accounted for variability, and we already accounted, well, if it doesn't perform well, what are we going to do? And we pre-design remedial measures. So it allows us to manage risk without a crisis. And if you ever managed a crisis, you know that's the best thing that exists for blowing your budget and your schedule big time and your blood pressure in the process. So, you know, if you design a monitoring system, if you see early enough, well, this isn't behaving as we expected or the way we like, you already have measures designed, you already know what to do, and you also make sure that it's still feasible to implement the most optimized measures. I don't want to say the pleasure or opportunity because it was the exact opposite, to participate in a project that desperately needed a tow berm, but there was no longer access to the toe of the dam. Abutments were very steep, they were in rock, and you name a crisis, we got one. So, as I said, it is an old concept, but the thing is, with the increase of the pace of business these days, with the fast computers and the absolutely excellent software that we have these days, there is a temptation to skip over some of the basics and turn on the computer, jump into the program, plug in parameters, boundary conditions, blah, 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 off you go. And this is a temptation that's going to only increase with the artificial intelligence, with AI. So the temptation in immediately jumping into the computer is to jump into the computer before you develop a solid understanding of the physics behind the problem. Oh, you got a draft version, that's nice. With my highlights. And actually what that is, it was in my draft for me to remember to tell the story that if you read the papers by Ralph Peck, he talks a lot about understanding the physics, conceptualizing the problem. And I actually had the privilege of working with him on a couple of projects, BNTM being one of them. And he kept on saying, the best way to start a design is for you to take an 8.5 by 11 piece of paper, a good old pencil, and sketch it up. What is it like? How is it going to behave? What's going to control this? What if this? What if that? Wrap the physics around your head and try to even estimate what's going to control that design. How much settlement am I going to get? How much displacement am I going to get? Draw a different angle. What do I expect this to do to the fact of safety? Things like that, for him was fundamental. And my reference here to wrong problem is because if you read his papers, there is a lot of examples that he provides of people who did a fantastic job, but solving the problem that wasn't the problem. It was some other problem, peripheral to the case. So it's very enlightening to look at that literature. So we all need to resist the temptation to jump into the computer first, define the physics that control the problem, spend time setting it up properly, and then you turn the computer on. And I'm not against computers, they are awesome. I'm of the generation that did seepage analysis and stress analysis by hand, and it's painful. I don't recommend. So these are pretty basic considerations that you probably all know. I'm just reminding you that go back to basics. But in geotechnical engineering, there are other considerations that we have to make. You know, we have to clearly define the problem, including all the requirements and all the constraints. Their physical constraints, their operational constraints, financial, schedule, regulatory constraints. And we have to define all of those. And that's basically the most important part of a design basis. People today, sometimes I see design bases that are a lot of things, but not that. A design basis needs to have more of that, your design criteria, what parameters you're going to use, but that's the fundamental part of the design basis that allow you to solve the problem to be solved and not something slightly different. So I already talked about the physics governing the problem. We need to know what are the critical elements, the key parameters, uncertainties and their impact, identify the potential failure modes, and then you develop and evaluate solutions for that. Look at the geology, determine material behavior, like nothing new. I bet you, like you all heard about all of these things. You have to define the parameters and account for the uncertainty. So if these are basic considerations that all designs have to go through. But I just want to highlight that this is not a workflow. This is a list of common considerations that you do. But we have to always remember that different problems require different considerations. But if you already figured out what your problem really is, think about those. And you could use this type of list, not necessarily this one, but this type of list as a checklist in the end, just to make sure you didn't forget anything. I'm not really a big fan of workflows because what I tend to observe, and I observe including happening to myself, you get into a workflow, you go, do this, do that, like that makes your brain turn off. It makes you not notice that, oh, this is different about this project. I also have to do X, that's not even on the list. So I'm not a fan at all of workflows. Yeah, people argue, make you more productive, make young engineers know what to do. I'm going to say this is a terrible way to start your career. Like, think first what you need to do, and then by all means, get this to like, or a list of some kind to see what needs to do. I think the more frequent use of workflows these days is actually impeding innovation. So, okay, that was my little soapbox. I'm not a fan. So there's other considerations that we need to do for a robust design, and one of them is serviceability. It's not because a design has a factor of safety of 1.3 that you're happy, because it may not work if the deformations are too large. Or foundation, yeah, the foundation may not have failed, but it's settled so much that's not meeting its intent. So, an evaluation of precedents and case histories. Like, there is so much to learn in precedent case histories. If somebody made a mistake already and had the courage and the vision to publish it, we appreciate and we learn from, so we have to take a look. And the other importance of case histories is that we take a little samples, even if we push a CPT, is that location, that little sample. But sometimes the entire geological formation is going to behave a little bit different. So case histories and back analysis allow us to have that kind of calibration. So they can't be underestimated. They're super important. The other thing about precedence is regional experience that we learn from. There are things that work in certain areas but not in others. And when we talk about precedence and regional experience, I don't mean at all do what everybody else does. I'm in favor of innovation and advancement of science, but all we need is not that we need to do what everybody else does, including the mistakes. Like, the things that didn't work. Very important. We need to develop a number of options so they can be selected, they can be compared. And we need to look at material availability and schedule, personnel, and local experience, because we are talking about a robust design being practical to implement. I am still working, but on this project in Mongolia, where, well, that's easy. Why don't you push a couple of CPTs here and there, and blah, 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 blah. And people go, what is a CPT? Oh, the nearest CPT machine is in Australia, 10,000 kilometers away. We don't know how to bring it here. So a good, robust design needs to be practicable and implementable at that place. So you need to look what's available around, what's the experience level. And sometimes, that again, we may push for innovation. Mongolia now does have CPT tests available, but you also have to see that the people there, they will need more support from the designers or from whomever to look at the data, to understand what it is, to see the procedures, to build something. So important to understand what's the local experience level and what can be done and what cannot be done, and what's new, it's going to need additional support. Okay, so these are now not common considerations for a robust design, but these are common design development elements. And maybe to some degree, to those of you who are not working on dams, or this might be a bit biased to one side, but I'm sure, like, even if you're doing foundations and other things, most of this applies. So those are I just picked 6 main elements here. So let's focus first on the first 3 ones. The design basis definition, the options development, and the integrity assessment and design. So we covered a little bit the business of design basis definition, and this is where you need to be a little closer to your client or to the owner of the project to understand the constraints, because most of those will come from the client, from the owner of the project. You have to be familiar with the regulatory environment and regulatory constraints in the area of the project to complete the design basis. And then option development, it is always good to start with as many as possible, and then use a technique like multiple account analysis or things like that, where you have a procedure to look at various aspects of each option and compare them with a thorough method to support the selection of the option. At that point, you go into the integrity assessment. That's more common, like we already mentioned some of those. I just want to highlight a couple of things. It is good to, after doing the site investigation and start to think about the design and the design parameters, to identify the potential failure modes. First of all, you need to identify them first before you get into the analysis, because it will affect how you set up your analysis. But then, by the time you plug in all the parameters and everything in your analysis, you may learn something. Oh, the lower factor of safety is not exactly where I thought, or this. So you may have to go back. So again, this is not a workflow, this is a list. You may have to go back. But I still support stopping and thinking about the potential failure modes, because one, you set up your computer model better. But even if you got it wrong, here's an opportunity to actually develop your engineering judgment. And this is an opportunity for you to think about the physics again. So next time you take your 8.5 by 11 as per Dr. Peck, like, you are notch better. So it's another question that pops up frequently, is how does one develop engineering judgment? Is by those cycles of attempting to estimate the results, doing the analysis, and then thinking, oh, how did my estimate compare with this? What did I learn? right? So we keep on coming back to that. And then the other thing that I want to highlight is in a group like ours, usually when you say site characterization, design criteria, we're thinking site investigation, drilling, sampling, what's the stratigraphy, what the parameters, but if you're managing a project, you have to remember that that's not just us, geotechs. The water resources people need to define, to do their site characterization. What's the hydrology? What are the orological effects? The geochemistry team, the hydrogeology team, they also have their site characterization, their select of parameters, their analysis. So it's not just us. And if you allow me another soapbox, you got to remember that analysis is not design. I can't even tell you how many projects that I review that people say, hey, I'm all done. Here's my stability analysis, my seepage analysis. I even done FLAC. Here's my design. No, that's not your design. This is just your analysis that supports your design. Like we're talking about this entire list of things to do, right? I learned this, I was just chatting before dinner with a group of longtime colleagues here. I learned that from Kent Kress, who I used to work with, and I just was so happy, oh, I've done my design. I did more than the analysis, so I was feeling pretty good, right? So I showed to him, and so I'm done. And he looks at the design, looks unhappy, and say, and where are the ramps? Which ramps? Well, people need to build this. Where are the ramps? Okay, I guess I didn't finish the design. So there is a lot to design. Ramps is one of them, but also there is the surveying, the schedule, what the kind of equipment, a lot of things. And if you have one backhoe of a certain model, how many trucks do you need? You know, you got to link up with the contract and say, how are we going to do this? Anyway, there is a big list, so just remember that analysis is not design. And when we do the analysis, we need to understand what exactly are we getting from the analysis. Besides the numbers, I want to focus on something else. So for context, I want to go back to Terzaghi in 1951. So in his words, he described the development of geotechnical engineering as having 3 stages. The first is the empirical stage, which is based on intuition and trial and error. Progress is slow, there's a bunch of back and forth, but people make progress. But then the next stage is the scientific stage. So that's based on an attempt to predict results with mathematical reasoning based on test data and fundamental relationships, which sounds pretty good. So at the outset, when we move into the scientific stage, the prospects of success, they appear to be unlimited because it takes time for the deficiencies and the limitations of the methods to become evident to people. So we all get very optimistic, but we need to remember that this is a stage, and then maturity is achieved. At that point, the limitations and the deficiencies of the analytical method now are being known, and they become tempered by evidence and by experience and by case histories. And at that stage, the restrictions imposed by Mother Nature on the theoretical approach based on math, reasoning, and fundamental relationships is tempered by experience, but progress at that time is achieved on a semi-empirical basis. So it sounds like a little backwards because you went to the scientific method and then you go back to semi-empirical, but that's the calibration to take into account the variability and the uncertainties that in geotechnical we deal with. So it's actually an evolution. And that's how it ends up being a more robust design, because tampering a good method with evidence and case histories allows us to make it in such a way that it is taking into account the variability. So Terzaghi has often emphasized the importance of not relying on physical and theoretical basis only, but also on experience and engineering judgment. So within that context, we need to receive the results of the analysis and understand each aspect of it and proceed accordingly. So to give very practical examples, I'm going to propose that limit equilibrium analysis is at a maturity stage. So in the 1950s and 1960s, Bishop, Morgenstern, Spencer, and many others, they were reasoning on the mathematical approach. Just go back here. And some fundamental relationships, and they develop a scientific mode. And then they also help us guide, Morgenstern particularly, but also more present to us here in Western Canada, or in Canada in general, guide us from the scientific stage of his own method into maturity. But now, maybe stress strain analysis, deformation analysis, flak, plaxis, and all this, that might be still mostly on the scientific stage, with some practitioners like pushing it into maturity. So these stages, obviously, there is a bit of simplification to that, but also they're not linear stages from one to the other one. There's quite a bit of overlap in time and space. So at the same time, there might be people thinking that whatever you got out of flaxes, that's the rule, and that's the number to second decimal place, while other people are just saying, yeah, but wait a minute here, case histories, like practical experience, and they're tampering the good guidance that we get from the scientific method and the computer with experience and engineering judgment, and landing on a robust design. At the same time, or some other place, there could be people still completely trusting the computer. So, but what is important is, in my mind, is within that context and understanding those stages, for us to stop and look and think, what am I getting out of this analysis? And then proceed accordingly to develop your robust design, which then involves a judicious consideration of case histories, or lack of. If you're doing something new, you need to be aware, hey, I'm the first, there is nothing for me to support this on. So it's an important consideration to take. Also, that you're encompassing the potential variability and the uncertainty with maybe more design cases, more sensitivity analysis, maybe with a slightly more conservative approach. And I'm not talking about here something overly conservative. And you need a targeted design of an instrumentation program that allows for calibration and validation of the model and to monitor structural performance. And things like tailings dams, for example, or dams or slope stability, or load tests on foundations, they're good for that. You run your model, you instrument, and then you see the results of either the instrumentation of your load test or the first stages of construction, and you go back to your model and you say, I'm not getting this, so you get to calibrate the parameters. So that's what I mean, proceed accordingly. So it's an important of making the design robust, managing risk, and managing the variability. Okay, so we're talking about those first three. So let's talk about the other three. So here I think we covered a lot of it here and there in different comments. But what is important here is that no matter how good your design is, You need to remember that the borrow material needs to be available, needs to be of the quality, have the properties that you assumed in your design. They're not too clayey, too sandy, too wet, that you get the quality and the quantity that you want. And it comes at the time that you want. If you need your basal drain, obviously to be built at the base of a dam, but that part of the borrow area that's got good sand is only at the end of construction, that's not going to help us. So obviously construction schedule and availability of material is really important. But another thing about construction schedule, if you assumed pore pressure dissipation, is it going to be dissipated by the time you finish construction, or are you going to have to make a difference allowances in your design? So all of those things, very, very important. But the bottom line is the entire list are elements that contribute to a robust design. So just to wrap up here, I'm going to give a simple example. So this is a very common cross-section of a tailings facility in the oil sands. So usually you got your structural part, which here is the compacted cell in orange. You get the rest of your deposit. You got your foundation stratigraphy. So for this example, we're going to focus on this thin layer, kind of white or grayish color, that's a clay, say a Pleistocene aged clay. So that's also a very common approach in oil sands. You define two design cases. A most likely case where you do your best estimate of the parameters of that clay, and you say you got a target factor of safety, 1.3 or 1.5, whichever is your design criteria. But then you also say, what is my reasonable worst case? How bad could this be? Not the worst situation possible, but a reasonable worst case that it could happen. And then you design for a lower factor of safety. You probably don't want to do like 1.0, but if you do the lowest bound, like maybe that's your number, but usually you give a little margin of safety because our design methods are not perfect, right? So here's an example. Let's say if these are all the data points that you have, your most likely case in blue is kind of, 50%, 33 percentile of the data, something common to use. And your reasonable worst case, the red line there is not the lower bound, the lowest bound, but it's down there somewhere. And you make sure that these numbers match or are reasonable relative to back analysis and case histories. And then off you go. You do your design for both cases. You try to match those design criteria for both cases. And then you implement the observational method. So you design your instrumentation program to monitor performance. You have your pre-designed contingencies. So in that case, a common thing is, say, if your reasonable worst case, or if your most likely case had a factor of safety 1.3, your performance is showing, we are not quite there, we might be more towards the reasonable worst case. Then the contingency measure is whatever it takes to bring your factor of safety back up to your 1.3 or 1.5 or whatever you chose for your most likely case. Then you implement those measures if you need. So here's the entire list of what constitutes the observational method. This is pretty close to just copying from the paper in PAC 1969. Just simplifying the words a little bit because the slide is wordy enough as it is. But those are all the things we've been talking about. He talks about exploration, most probable conditions. He talks about unfavorable conditions, selecting in advance. And this is important to go back to this because there are people out there who think the observational method is you design whatever you design, you look, if it's not good, then you figure it out. No, this is a method. I make the point in every report that I look at or that I write of capitalizing observational method because it's not just look and then figure it out, right? there is something to be done that you need to do here. So that's pretty common in deformation when we do limit equilibrium analysis. But I also want to point out that if you do performance-based design based on deformation analysis and allowable displacements or allowable deformation, that's not an option. You either use the observational method or you do the performance-based design. If you go through this list here, there is nothing here that tells you what method to use. There's nothing here to say use limit equilibrium analysis or use a FLAC analysis, a deformation analysis. This is simply an approach to manage variability, uncertainty, and risk. So these days, performance-based design is the cool thing to do. I think it's cool too, but it's being said as you either use the observational method or performance-based design. Not at all. You manage risk and uncertainties to develop a robust design by using the observational method, and then you could either use limit equilibrium analysis or you could use deformation analysis, with the difference that the design criteria is certain fact of safety, which unfortunately you can't measure the fact of safety in the field, so you need proxies or other things to decide whether you are in one design case or the other design case. There is empiricism to say, well, at a fact of safety of 1.4, you shouldn't be seeing any displacements, but 1.1 might move more. Or in other regions or other materials, well, no, maybe 1.4, you're still going to see displacements, or 1.3. So there is empiricism and engineering judgment, but your design criteria is something that you can't actually measure in the field, while performance-based has the advantage that you can actually measure displacements, and this is what you want, or your design criteria, or not. And foundation engineering is ahead of us in, say, dam design or slope stability, because they had this kind of design criteria before we did. So that's what I wanted to say. So just to wrap it up, in the example that we had, there are many things that when we approach it that way, we can defend that. If somebody says, do you think your design is robust? There's several things we could say. It is a risk-informed design. Again, not just a performance-based design is risk-informed. Our limit equilibrium also is risk-informed. We have in full implementation of the observational method. We got instrumentation. And the instrumentation program is not just having the instruments in the ground. It's having them at the right place, properly installed, measured with the right frequency, the data analyzed properly. That's what an instrumentation program is. It's the whole package, right? So seepage is collected and controlled. There are multiple lines of defense. This is a robust design regardless of the approach that you take. Okay, that's what I wanted to say about the robust design.